Allora, buongiorno a tutti e a tutti, sono Massimo Leone, il direttore del Centro per gli Studi Religiosi della Fondazione Bruno Kessler. Scusate per i ritardi e per i problemi tecnici che abbiamo avuto, non è sempre facile gestire queste attività ibride. Oggi abbiamo il grande piacere, I'll switch now to English after the few words of introduction in Italian, to have an encounter between two research centers and above all two research centers that focus on different domains of knowledge. And in particular, we have the great pleasure to have the director of FPK ECT, Professor Ubirajara from Kolck, addressing us with a talk that we really look forward to. And to have discussant another director of the POVO area, Richard Hall-Winton, director of ST, Sensors and Devices. So just a few words on the main speaker, Professor Ubirajara, also known as Vira, Van Kolck, with directeur de recherche de classe exceptionnelle at France CNRS and professor of physics at the University of Arizona, just to give you an idea of its international scope. He's also currently director of ECT FPK after receiving his PhD in 1993 from the University of Texas under the supervision of Professor Weinberg. He held postdoctoral and research faculty appointments at the University of Washington and Caltech. He then joined the University of Arizona in 2000 and was a Riken Biennale Research Center Fellow, a US DOE Outstanding Junior Investigator, as long Research Fellow before joining the prestigious CNRS in 2012. He was then also elected Fellow of the American Physical Society in 2004 and member of the Accademia Europea in 2020. He received the 2015 Prix Paul Langevin of the Société Française de Physique, the 2019 Kofler Prize in Research at the University of Arizona, and the 2020 Hermann Festbach Prize in Theoretical Nuclear Physics of the APS. So we're really thankful that you and Richard have found time in your very busy schedules to come to Santa Croce. Today we're going to start with a presentation on coincidences in physical theories. Of course, coincidences are an object not only of physics, but also of other disciplines, philosophy, theology. I'm not sure that we talk about the same things when we talk about coincidences, but we'll try to understand each other and to dialogue. So without further ado, also because we're a little bit late, I thank you once again, all the participant members of the various centers who came here, who are online. I apologize once again for technical difficulties, and I give the floor to Vira.
Okay, thank you. I guess I'll be seated. It's not a standard thing in physics, but I think it's perhaps better for a discussion. Thanks, Massimo, for the nice introduction. What we are trying here, there we go. It's something a bit different from usual. We've been reminded over the last week or so that the late Papa Francesco encouraged us to build bridges, and that's the spirit of this presentation. Try to build a bridge between what some of us do in physics and perhaps some ideas that the humanities might have about similar problems. I will apologize in advance if I'm too technical at times. Yes, so it's very important that you stop me. And apologize also, we have physicists here, apologize to them for sometimes simplifying things too much. But So they are not going to go very far. This is the outline of my talk, which hopefully leads to some discussion from both communities. First, some statements, some observations about what is currently the paradigm for theory construction in physics. That paradigm, in fact, is something called effective field theory, which I will explain, trying to be as qualitative as possible, and then discuss, because this framework sort of sets the stage for what we call fine-tunings in physics, but also I think if we can use the word coincidences in a general sense, coincidences in physics. Then I'll discuss both coincidences at supranuclear energies and nuclear energies, and then go beyond science, or perhaps established science in part, and hopefully that leads to discussions a bit beyond what we do in physics. So let me start with a remark from my former advisor, that frequently in physics people use arguments of simplicity to develop theories. Stephen Weinberg remarked that even simplicity has to be explained. So what the idea of explaining something is to have a general framework that applies in different situations, and when you apply to a specific situation, if you obtain the results that are known to be approximately correct in that domain, then you are explaining those results from the more general framework. So this was this framework in physics currently is what's called effective field theory. It's been around already for almost 50 years. Already in 1993, you already saw philosophers discussing this changing paradigm as for what theory construction is in physics. There was something before called renormalizability, for most of you that probably doesn't mean anything, but take it as a framework that justified certain aspects of the theory construction. And this idea has been superseded by what's called effective field theory as a general framework for analyzing experimental results. So the idea in qualitative terms is that the concept of effective field theory is larger than the framework of what are called renormalizable theories. In many cases, like in the standard model of particle physics, which provides us with the best explanation for physical phenomena, the effective field theory gives the renormalizable interactions as the main contributions, but then there are corrections, and one can account for this correction systematically. And so the framework is of effective field theory, or EFT, is larger, and therefore it explains the renormalizability criterion that people used to have, because it's, for certain theories, it's what comes from the more general principle of EFT. So EFT is something that has developed in physics for a very long time. The roots are even before the Second World War, and the work by Euler and Heisenberg, and it had a very long evolution, and it was crystallizing what Weinberg again called the Kolck theory. Now, this is a bit technical for many of you. I'm going to sort of try to give a more qualitative picture soon, but just so that you see what the principle is. This Kolck theory is an expression that it's not a theorem in a mathematical sense. It has not, or perhaps cannot be proved, but it's something that we know no counter is example for. That's a word fault in there. And the idea is that you can produce, so physics, especially after quantum mechanics, we understand that we have to focus on quantities that we call observables. Those are quantities that can actually be measured in a lab. In a theory, you might have you frequently or always introduce other quantities that are auxiliary, intermediate steps, but the quantities that we can have certain as physicists about are this quantity called observables, and these observables are obtained from something called the S-matrix. The S-matrix is an object that incorporates the information about the scattering of particles. So you strip a physical system to its bare minimum. So you have particles, they come from very far away where they are free, they get in contact and they go away where you have a detector. And by measuring properties of this scattering with the information about this object, the S-matrix, and this effect field theory is that the most general S-matrix can be obtained from the most general quantum field theory with given symmetries. And in addition, because the S-matrix is calculated from quantum mechanics, incorporates special relativity and so on, it also has these other general concepts. So the idea is that we start from the most general dynamics allowed by symmetries in order to calculate observables. Now, in a more qualitative fashion, an EFT has 4 elements, I would say. One is that we focus on the relevant degrees of freedom. What are the degrees of freedom? Those are the basic objects that we are going to use in our theory construction. So let's suppose we look at this square there. So a physicist would tend to describe what's happening there by a set of points, or actually a set of approximate circles of different colors at different positions. So a physicist would put a grid X and Y and would say at X equals 4 centimeters, Y equals 5 centimeters, there is a blob, a black blob. And so then go on and describe each one of these blobs. And that would be a complete description of the system. So in this sense, that would describe this picture that we see in terms of degrees of freedom, which are dots at certain positions. However, that description is tied to our resolution scale, or to what we are seeing. Suppose that you want to describe the same region of this picture here. Then, so this is a detail of Leonard Soha's paintings. To describe the same region, it might be more effective to say that is the mustache of a person. So if I'm interested in describing the picture as a whole, my effective degree of freedom might not be points or dots, but mustaches, noses, eyes, and so on. And that description might be convey much more information if we are interested in these larger distances. So the first ingredient of an effect field theory is that one should choose the coordinates to describe a system or the degrees of freedom that are appropriate for the distance scale or the energy scale in physics, energy and distance are more or less the inverse of each other. It's we should choose the coordinates or the degrees of freedom that are best adapted to the scales that we are interested in. So this is the first ingredient of an effect field theory. The second is what I mentioned already, emphasized already, is that among these relevant degrees of freedom or effective degrees of freedom, we want all possible interactions. Let me give you an example, which is not quantum mechanics, it's just classical mechanics. A three-body system consisting of the Earth, the big blob there, the Moon, and a satellite orbiting around the Earth. Now, I described the radii of the Earth, and I give the numbers for the radii of the Earth, 6.4 million meters. Of the Moon, 1.7 million meters, and the distance between them, which is 384 million meters. So if you compare those numbers, you see that my drawing is way out of scale. But I had this drawing to illustrate one effect that us physicists know very well, which is that in addition to the interaction that the Moon and the Earth and the Moon have that orbit around each other, the Moon creates tides on Earth. And it's known that the tides actually have an effect on the motion of the satellite. So this is a view where we see the Earth as it's, let's say, rigid, as a rigid approximate sphere, but with tides around it. Now, the actual picture is a bit more like this, and even that is out of scale, right?
Especially the satellite is
Especially the satellite, because even here, the satellite is out of scale, but here I couldn't make a even smaller point that's visible. So even the satellite is out of scale. But the situation is a little bit more like this, that for the relevant distances in the problem, the Earth is very close to, even the Earth is very close to a point. So if I want to describe the dynamics of this three-body system at this scale, where I treat the Earth as a point, how am I going to have to account for the effect of the tides, which are generated by the Moon, or the effects of the tides on the satellites? Well, we do that by something that might be a bit less familiar to people, which are three-body forces. What are three-body forces? Perhaps the best example is something that used to be on Wikipedia, then I think it was removed maybe because of
gender issues.
Yes, probably. Maybe it's going to come back now. But there's nothing sexist about this. It's just jealousy is a three-body effect. A three-body effect is anything that disappears when you remove one of the three bodies in the problem. So jealousy is something that will disappear in a situation like this. It will disappear if I take any one of these three people out of the picture. So the lesson from this is that once you have this changing resolution, because I'm going to adapt my theory to the resolution that I want, when I have this, I have to allow for the most general interactions that I can have. Even if at a very fine resolution, I can describe my system in terms of two-body forces alone. In terms of smaller, I mean, a less good resolution, I will have to include 3-point forces in this example. So in general, I have to allow for all the possible interactions. One way to say this is that what's not forbidden is compulsory. So this is a principle in physics. And this was in part came to the fore of the physicists' minds because of quantum mechanics, because quantum mechanics allows a number of processes that we call virtual. So everything that's not forbidden is compulsory is the second element. The third element is, which is vital, is the one of symmetries, because it sounds like, well, if everything sounds like I would have to include a whole lot of things. And so symmetries will play a restrictive role in theory construction. And
it's an essential. Symmetries are an essential. So
they are a constraint in the system. So I am going to, well, let's first, I'm going to explain this by a joke that all physicists know, but perhaps it's not known outside physics. It's a famous joke where someone, a farmer, is having trouble with with milk production and comes to 3 scientists, a biologist, a chemist, and a physicist. And there are all the variations of the joke where the 3 different the sciences are from all the fields. But the joke more or less goes like this. The biologist thinks that the cow must be sick and tries various antibiotics and other medicine, and the cow still has a problem. The chemist thinks, well, there must be a chemical imbalance, and so also assign some change in the nutrition and so on of the cow. Also doesn't solve the problem. Then comes a physicist and says, oh, this is a simple problem. First, we take the cow as a sphere. And us physicists, typically, maybe not every but most physicists like this joke because it actually does reflect what we do in physics. Sometimes we simplify things tremendously, but in this particular case, there is a technical reason for the simplification. So the idea is that if you want to describe the cow, well, okay, we probably many of you don't know vectors, but so maybe this technical explanation here is a bit too much, but qualitatively, it's much easier to describe a sphere than to describe a real cow. So of all the possibilities that you have to describe the object, for example, if you have 2 of these vectors lying on for the dynamics of the cow, they are going to be constrained if you have spherical symmetry. Now, this joke often continues with, then we treat the head and the tail in perturbation theory. So perturbation theory is something that's essential also to physicists. And the idea is that frequently you do not have a full symmetry, but you have small breaking of the symmetry. For example, the head makes a cow not quite a sphere, but the head is relatively small compared to the rest of the body, so you treat that as a small correction. And that's what's called perturbation theory. So in this more technical case here, if you have 2 vectors, you're going to have different combinations of these vectors that were not present in the case of spherical symmetry, but they are going to be suppressed by a small parameter, and that will allow us to have a quantitative description of the deviations from the symmetry. So the role of symmetry is to say that not everything is allowed. So if we have the case of spherical symmetry, not all possibilities are going to be allowed, and that is going to restrict what otherwise would be too many interactions. Now, the final ingredient is the one that's more related, leads us to the rest of the talk, which is a bit less well known even within physics, is the fourth ingredient is what's called naturalness. So naturalness is a concept that evolved in it existed in physics before, but was sort of formalized in the late 70s by Kolck and Feldman. And loosely speaking is that in a system, you're going to find certain scales. For example, in my spherical cow, it's going to be the radius of the cow, right? Of the cow. So there are certain scales in the physics. I'm going to allow all the interactions allowed by the symmetry. So I'm going to have in principle an infinite number of parameters. So I need to make an assumption about the magnitude of these parameters. And the assumption is that once the scales have been factored out, a few of them, maybe just one or two, well, I will have at least two, then all the parameters that remain will be of order 1. What order 1 means? Order 1 is a concept, is a qualitative concept. The numbers are going to be, by dimensionless, I mean they don't have, they're pure numbers. And of order 1 means that they are not too different from 1. They might be a half, they might be 3, but it's unlikely that they are going to be 10 or 100 or 1 over 1,000 or something very different from 1. One example, which doesn't matter how it's calculated, but for the physicists in a spherical well, if you want to have the size of a bound state, you are going to see that it's going to be typically of the size of that well. But in general, it's that you are going to have if you have an underlying theory and you calculate the parameters of the effective field theory, they are going to have a probability distribution according to what happens when we vary the parameters of the underlying theory, and that distribution is going to be peaked around 1 for dimensionless quantities. The structure of how this peak happens will depend on the underlying theory, how broad, whether it's just a peak or something more like a broad bump, or maybe 2 bumps at 1 and -1, or something. The details will change, but the idea is that the parameters will be over 1, unless they are suppressed by a symmetry, like the head of the cow is small because of the spherical symmetry, approximate spherical symmetry of the cow. So this is the principle of naturalness. And what's the justification? Well, justification is from our good old Occam principle that one should not, maybe this, maybe we will to break this idea, that we should have one principle, that we have an infinite number of parameters. We should have one principle to guess the size of all of them. Otherwise, we will have a problem of every time we have a new parameter, how are we going to guess its size? So it's the simplest assumption because it applies to all parameters. Now, I'm not going to justify it, but maybe make it plausible, that I mentioned that there were some scales. One scale is always going to be what I'm going to call here the energy scale of the underlying theory. My effective field theory has a certain resolution. It will fail when I go to small resolutions in terms of distances. That's high energies. So that scale is always present. Then I'm interested in low energies or large distances. So that's the scale of the process that I'm considering. So I'm going to always have at least those two scales. And the idea is that if everything is of order 1, then the only ratio of energies that I have will be the energy of the process divided by the high energy of the underlying theory. And therefore, the theory will allow, even though it has all the interactions allowed by the symmetries, it will allow me to have a perturbative expansion in this small ratio, the energy of the process, which is smaller than the high energy. Now, this is the simplest assumption, and the idea is that, well, we see how it works, and if we have to revise it, we do. And when that happens, that's what we in physics call fine-tuning, but I think it's appropriate to call it in certain cases coincidences, and that's the rest of the talk. So the idea is that in physics, we now see the world as a tower of effective theories in which that are ordered according to the increasing energy or decreasing the distance. And I put in the slide a bunch of these effective theories. I put an axis here, which is energy, something called GeV. That's giga-electron volts, which is 10 to the 9 electron volts. If you don't remember what an electron volt is, doesn't matter much. Just the 1 GeV is more or less the mass of a hydrogen atom. And associated with this energy scale, there is an inverse distance scale, which I put in meters. So we're talking about very, 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 very small distances here. So all that I have here are effective theories for nuclear and supranuclear energy. If I go in the opposite direction, I go into the regime of atomic physics, molecular physics, condensed matter physics, and beyond. I'm going to be talking mostly about what's in the nuclear in supranuclear part of this chart, because we now have a effective field theory called standard model effective field theory that provides an explanation for almost everything that we see in the world. As the energy decreases, let me see my pointer here, we have a sequence of effective theories that have a root on this standard model effective theory. What happens in the other direction, we don't know very well. There are some indications that there might be something called a Gremlin-fied theory or gut at a scale of order 10 to the 15 GeV, and at a scale of the order 10 to the 18 GeV is what you suspect general relativity as an approximately classical theory breaks down. What we probed so far in physics is maybe somewhere around here, 100 to 1,000 GeV. So Richard and his friends, the particle experimentalists, probe physics up to a scale around here, the LHC, or indirectly for other low energy experiments, you can get some information about the interaction of the standard model EFT. But we are somewhere a long way from what we can reasonably say with some certainty they're going to do, where the extensions of the standard model are. But anyway, this is the vision now of physics as the sequence of effective theories, and we don't have to worry about the specific details. But I do want to point a few things out. First of all, is that, well, most important of all, is that naturalness, this concept that I mentioned, seems to work for the vast majority of parameters for most of these effective theories. I'm not going to spend time on this because it's not the issue of the coincidence, which are the departures from naturalness. But for example, it explains why you expect neutrino masses to be the first observed deviation from the standard model, and voila, the neutrino masses are so far the only observed deviation we have. It explains why the weak interaction is weaker than electromagnetism, and so on and so forth. So naturalness in general works. So what I would like to talk is what I, for this talk, would like to call the problem of coincidences, which is that there are a number of significant exceptions in preparation for what's coming later. I'm going to call mini except with a question mark.
So that's a question.
Yeah. So I think this was
semantic clarification. First, before you mentioned the word perturbations, so perturbations and coincidences, what is the relation? The same thing?
No. No. Perturbations are simply corrections to a main picture.
Okay.
Okay. Now that main picture already, does it have small adjustments that or coincidence among different aspects of that picture? So the perturbations are going to essentially be irrelevant for this talk. I'm worried about, in the main description, failures of this naturalness.
Okay.
Does that make sense?
Yeah, absolutely.
Okay, this is, but this is a good sort of point for maybe more questions.
Please, Boris.
Yeah, just, another terminological question. This expression, effective degrees of freedom, you introduced it, and your examples were like, you can, for instance, when you have just a very tiny bit of this painting, you can have dots,
Right.
Or if you look at the larger picture, you can talk about mustaches and eyes and so on. So why do you call this effective? What does this have to do with freedom? It just seems to be the choice of
Scale.
of vocabulary or scale. So why freedom? Just
Okay, now this is a technical term, I guess, in physics. Degrees of freedom are the objects that we are going to use as basis for our description.
okay. So
And what I mean by effective is to reinforce this idea that the choice of these objects depends on the scale that I want to describe.
okay.
For example, you might have heard that there are some people in physics that developed string theory as an attempt to describe physics at the finest possible, the smallest possible distance. They are going to then formulate this theory in terms of objects called strings. But if I want to describe the dynamics of us in this room, it would be a waste of time to describe this in terms of strings. Because approximation or interactions might be described in terms of individual human beings, right?
Or spheres.
Or spheres. Yes. So that's what I mean by effective and by degrees of freedom. Degrees of freedom, because these are the objects in physics that are going to move, right? So be dynamical and are going to interact with forces.
Thank you.
Any other questions?
Okay, so I'm going to get a couple of examples, starting from examples from the standard model effective theory. I mentioned it's an expansion in powers of E over E high, the energy of the process divided by the breakdown scale. And in this theory, it starts at power -4. Now, what I wrote here is a Lagrangian, which you guys have probably already what you don't. That's for the physicists. So I said that in EFT, one has to start from the most general Lagrangian. This Lagrangian can have a term that's called the cosmological constant. The cosmological constant is, you can think of the energy density of the vacuum. In quantum mechanics, the vacuum, I mean, you remove all of us from this room, you remove all the air molecules, you still have a medium called a vacuum. The vacuum is not inert. Particles can virtually appear and disappear in this, from this vacuum. So the vacuum itself has something called energy density, has energy, and therefore the energy per unit volume is an energy density. Now, this is the cosmological constant is very important because it's the lowest power of E over E high. It controls the dynamics at very, very large distances or very small energies. And therefore, it controls the dynamics of the universe. So if the cosmological constant is negative and very large, the universe very soon starts contracting very soon. The cosmological constant is large and positive. The universe expands very quickly. Now, therefore, from statistical observations, you can infer a value for this cosmological constant. Now, for the physicists, it could be that this energy density of the vacuum is a more complicated thing than just a constant. And particular results from a couple of weeks ago from DAISY telescope suggest that they might be dynamical in some way, but in the simplest picture is a constant, and it can be determined. And it's a tiny number in these units, GeV. Again, it doesn't matter so much what GeV is, but it's a tiny 10 to the -42 in these units. And naturalness suggests that this object is given by the Planck scale, that scale where general relativity becomes quantum. And so there is a discrepancy of 60 orders of magnitude. So something that you'd expect to be order 1 is 0 followed on dot, a 1, 60 decimal places away, so 0.00000 instead of 1. That's tremendous. So you can say that the cosmological constant, to a good approximation, coincides with 0. So it's a coincidence in that sense of 0 is a special value, but not what naturalness gives. The next term in the expansion also has a problem, is something called the Higgs mass. And again, it can be determined from experiment and from naturalness arguments. You'd expect to be of the order of this scale of the Bernoulli 5 theory. And here the conflict with naturalness is much less severe, but it's still very large, 10 to the 13 order. So again, we can say that in the natural scale set by the gut scale, the Higgs mass almost coincides with 0. So these are big problems, because those are the first two problems, the two most important interactions in terms of this expansion E over EI, or would be the most important if there was no fine tuning, but they are of course suppressed by this enormous amounts.
And this also has nothing to do with experimental conditions. So.
No, so the experiment determines, for example, this value here for the Higgs mass. So Richard goes to his lab and he measures the mass of the Higgs particle to be 135. And this is a prejudice based on naturalness, right? So just like with the cosmological constant, this is something we measure from astrophysical observations, and this is the expectation based on naturalness. So this is complex, in large complex. In effect, these naturalness problems have been guiding most of the research in particle physics for the last 50 years or so. In part because they have had particle physics, very little data to guide the research. And so theoretical problems came to the fore, but it's been really the main guide in theoretical particle physics for many, many years. So perhaps it's fruitful to look at coincidences at lower energies where we know a little bit more about the underlying physics. So for the next few minutes, let me talk a little bit about coincidences at nuclear scales. With actually the classic example of how we do characterize coincidences, which is carbon and oxygen formation in stars. So as you know, carbon and oxygen are very important for our kind of life. And it's understood that carbon and oxygen are formed basically by two reactions. One is one in which you have three nuclei of helium. So the nucleus of helium consists of two protons and two neutrons. That is also called the alpha particle for historical reasons. And so the first step is the formation of carbon when three of these alpha particles collide to form carbon, which has the same number of protons and neutrons, 12. So 6 protons and 6 neutrons. And a particle of light, called a gamma ray. So in chemical notation, 3 alpha particles goes into carbon plus a gamma ray energy. That's the formation of carbon. But then in carbon, another alpha particle can come and collide with the carbon that has been formed and produce oxygen with another emission of energy in the form of gamma ray. Now, we observed, so now astronomers can go out and measure the abundances of carbon and oxygen in the universe, and they found that it's about half. Twice as many oxygen atoms as carbon atoms. Now, it's a lot of theory, which I'm not going to go into, and it's quite old, but has stood the test of time, that in order to achieve this balance of carbon and oxygen, there is a minimum rate that you need to have for this first step. Because if it's too slow, then one needs to accelerate these alpha particles more. So we need more higher temperature. But then it's also easier to destroy the carbon that has been formed because the extra alpha particle here also has a lot of energy and can destroy that carbon. So there is a balance to achieve this observation.
So
Yeah.
was
Sorry, BE?
stays for
Very. Sorry. Yeah, I'm coming to that actually. So this is a very interesting process and has captured the imagination of many people, including outside people, outside science, because this first step then is very crucial and it's very delicate. So it relies on something called resonances. So in physics, you have some objects that are called bound states. So I have an electron and a proton, they form a bound state of a hydrogen atom. It's a unit that can live for a very, very long time, perhaps forever. Resonances are objects that form for a while, but then they disintegrate. But during the time that they are nearly together, it's easier to, the reaction is much stronger because the particles stay there for a while before they disintegrate. And in particular, in this reaction, if two alpha particles form a resonance called the beryllium 8 resonance that lives for a long time, it's easier for the third alpha to come and hit these two particles and produce carbon.
our eyes are very open because resonance is one of the most important concepts in social theories nowadays.
Okay.
And
So that's might not
all of us are
resonances. But on a very basic level, resonance is let's suppose we get off in a discussion, and that discussion is very intense. We are resonating in terms of ideas, right? So in that sense, that's what the resonance is. It's an increase in this interactions, so the process of scattering of these two particles.
that's the physical definition. So the standard definition is almost translates the represent candidates.
Yeah, yeah, maybe my physics colleagues will disagree with that. But qualitatively is what the resonance is. So again, so if I plot the possible states of beryllium 8 as a function of energy, and now I'm using a different unit. This is a million electron volts, not giga-electron volts, which is a billion. So this is a million of electron volts. And you see there are excited levels, there are resonances, let's say, of the alpha-alpha scattering processes at various energies of order 1 in this scale MeV. But then there is a very resonance at very, very low energies. And that's the beryllium 8 ground state. And that facilitates this process. You see that state compared to the 2 alpha state is 0.09, let's say 0.1 MeV only, much smaller than the scale that you'd expect for resonances. So already there, we see an almost coincidence with 0. Nevertheless, this is not sufficient to get the observed carbon to oxygen ratio. Hoyle in 1954, actually a bit before that, the publications from 1954, he predicted that another resonance was needed for this reaction to give the observed carbon to oxygen ratio. And even made a prediction for more or less which energy this extra resonance should be. And then he walked down the hall, when he walked down, he was visiting Caltech, and walked down the hall to a Richard Light person, an experimentalist, and told them you should look for this resonance at this energy. And voila, these people found it at, again, a very low energy. So this is now in thousands of eV. But again, just look at the levels of carbon-12, the threshold or the minimum energy for 2 alphas, I mean, the resonance beryllium 8 plus 1 alpha is here. In this state is very close to that that other state, the free state. If you notice the date, the experimentalists actually published first, and that's maybe one reason here should be careful in the talk. But this was a great.
Doesn't happen very often.
So again, now this is on my way here. So again, we have a second almost coincidence with 0 in this case. Now I'm going to skip the next slide. Well, first we all have to get there. Because it's a bit technical. People have looked at how much of a coincidence this is, but it's kind of hard to say even looking in more detail. So let me skip this slide a bit technical. Also, let not me go through this slide in detail, just make the point that now we went to very low energies with the hope of being able to explain this coincidence from something a bit less, a bit higher energies. So we are working, we as a community, on trying to explain these two coincidences, and we have gone some way into that, but we're still working on it. If you look at 3 nucleons of protons and neutrons, again, in terms of energies for the system of 2 nucleons, 3 nucleons, 4 nucleons, the energy scales are something like this. And let's not go into look at too many of the details, but there is a coincidence here that there is a 4-body excited state very close to 2 3-body excited states that are very close together themselves. We understand why these 2 states differ a little bit in energy, but why this guy here is in the middle is a bit surprising. And what we notice is that the 2-body energy is relatively small compared to 3 and 4-body energies. So that suggests that maybe we can go to a spherical cow. The spherical cow here is simplifying the problem, taking this level here to be 0, to simplify that. So this is a cow without a head. This is a head. All right. See what we get in that case. The calculations are simple. This is what's called the unitarity limit. So it's now a theoretical calculation. And for the 3-body system, what we find is a single state here at this level, in a sequence of states. While in physics there are, in real physics there are a couple of states there. So we get something similar. For the 4-body system, we also get a similar situation, including a level that is even closer, even more of a coincidence that we see in the physical case, which suggests that this picture explains that coincidence because it comes out naturally. And you can trace this to a symmetry, which is not obvious a priori, which is something called discrete scale invariance, and it's what underlies fractals. We now know that it also, the same theory, generates some of the coincidences that I've talked about, in particular the small energy of that alpha or beryllium weight, if you want, excited state. And we are working on trying to see if that explains also the small energy of the 3 alpha Horner state. That wouldn't solve completely the problem because there's still, these calculations are done numerically, so it's very hard to get a sense of what is really causing this, but at least it would come out of the field automatically.
In the picture, it will be faithful to this numeric data, so it will be identical fractals, or the
Yeah, so, but the way the fractals appear, it's a bit technical. It's that this state here, there is a sequence of states. So this here, there is a sequence of states, and each state is like this divided by 500. Okay. So here in this fractal, the idea is this area here is that picture divided by 9, not 500. Okay. But that's sort of the analogy. Fractals, what's technically called scaling fractal, has a single scale that you start with, for example, this picture, and then a scaling factor that makes each piece reproduce the bigger picture by that factor. So in this case, the scaling factor is 9. In the previous picture, the scaling factor is 500, so I cannot even show it here. So anyway, we are making progress, but in this coincidence, but the problem of the other coincidences with it. So let me just finish with some very general stuff, which is perhaps very naive, more in the direction of what you guys might be interested. How are we going to, at this point, as I said, there are coincidences in cosmological constant and the Higgs mass that we don't understand and have resisted explanation. Maybe they will have an explanation in terms of emergent symmetries that we don't understand. But people have tried to understand this in other ways. And one is what's called the weak anthropic principle. So the idea is that it's not values of physical quantities are not equally probable. But they take the values that are restricted by two requirements. One, that we exist and we can measure this couple of constants. Right? And second, that the universe must be old enough for us to be here and measure this couple of constants. Right? So an example is, again, Weinberg provided an estimate or a limit on the coupling of the cosmological constant. Because if the cosmological constant is too large, then one does not form gravitational bound states, galaxies, and planetary systems, and so on. And therefore, it's hard to imagine our type of life. So essentially what he said is he put limits on the cosmological constant lambda, given the fact that we exist. So in terms of probability, he made put constraints on the probability of our existence given values of the cosmological constant. Therefore, given that we exist, limits on the cosmological constant.
A little bit Cartesian. It's a little bit, I mean, it's impressive how it is centered on our own existence.
Yes, exactly. Exactly. And so that creates lots of debate within physics, how relevant one should take this principle to be. Or to some extent it's an obvious thing, but it does provide an inference about the values of coupling constants. But of course, what we want for these discussions of naturalness is the probability for lambda, given the fact that we exist. And then if you use Bayes' theorem, that is the probability that we exist even a cosmological constant times the probability of having cosmological constant a priori. And for that, we need something else. And that's what's provided by the multiverse, which again is a somewhat controversial aspect of physics. but it's something that has captured the imagination outside physics. So the idea is that if there is a collection of universes, then in principle there could be a distribution, an a priori distribution for all the parameters of the theory. For example, the cosmological constant. Now, this is controversial because people say, well, we're never going to measure other universes. But if we have a theory for these probabilities, and if it explains not only the cosmological constant, but other observed values for parameters, for example, like the Higgs mass, it will have scientific predictive power, and therefore be falsifiable. So in a sense, it would be similar to what I call quarks and gluons in physics, which are also philosophically a little bit of a controversial issue, or was a controversial issue at some point, because they are not observed directly, but we can make predictions based on them, and therefore we assign reality to them, or they are effective degrees of freedom. Now, going further afield, more maybe towards the connection with the center here. I said that I was going beyond science, right? An alternative is, at least philosophically correct, is intelligent design. The idea is that if you know nothing about the a priori probability, or if the a priori probability for two hypotheses are the same, then you prefer the one which has the highest likelihood. So the probability, if you assume a hypothesis that probability from that hypothesis to give the observation is higher than another hypothesis, you prefer that hypothesis. It gives a highest likelihood. So the famous example is by this guy Paley in 1802, although you can trace some origins of this way before. He gave the famous example of walking on a beach or whatever and find a watch, right? And the two hypotheses that he said were, well, one is the watch was built by an intelligent designer. The other one is that the watch is a product by chance. You say, of course, you see a watch in the middle of nowhere, you haven't seen a designer, but you infer a designer for that. So then, big leap. You replace the watch by fine-tuning in a resonance position. Right? It does look a little bit like someone adjusted that, put that resonance over there, and that's sort of the idea of intelligent design. And this has, in the late 90s and 2000s, was sort of a revival of this sort of arguments. But as it was pointed out in many discussions, whereas for the watch, maybe one can estimate its probabilities pretty well for a resonance position. We have all sorts of problems this probabilities. Now let me finish with another perhaps pseudoscientific idea about coincidence. There was a period when I was reading this a lot about intelligent design because I was very interested in the problem of naturalness. And I was reading a book, in fact, this is where this article by this guy Sober is. And I finished the book and I was in Brazil and I needed to find something to read, and I walked into my parents' library. They had a huge library of psychology books. And I had done this many times before. I never found anything useful to read there for the psychologists. But then I found this little book that day. I found this little book called Synchronicity by Jung, right? That in itself was a synchronistic event.
Serendipitous.
Yes, but the idea of for synchronicity is that some psychological states and some external objective, whatever you want to call states, are linked by something other than a causal principle. I think we all have had this sort of experiences in our lives, right? That two things happen close to each other in time in this case, but they seem to be meaningful. And so Jung gave this example of treating a patient that he had not made progress in treating this patient for a very long time. Then one day the patient described a dream about a scarab, and then at the very same time a golden beetle appeared at the window. And once Jung pointed that out to the patient, after that, treatment was very well. So what are the chances of a golden beetle appearing at the same time that the patient is, right? So this was sort of what was in his mind. So the idea is that, well, if you have a probability of two events happening, there's a probability of one, and then the probability of the other one, given that the first one happened. If the two events are independent, then this probability here is just a probability of the second event, A. So the inference from Jung is that perhaps that probability is not the same whether the first event happens or not, because they are linked somehow, just not causally. But obviously that's what's pointed out by statisticians and maybe even psychologists, is that there is a large number of pairs of events that happen in our lives. So it's not surprising that occasionally two that are meaningful happen at the same time. However, still many people have a feeling that those are special events of some sort, and maybe that they come also very often close together. I mean, Jung also relates an example, like many other examples, where a number appears repeatedly within an hour several times, right? So this takes us really very far from physics, but these are issues that have been brought up. So let me just summarize, no conclusion. What I try to convey is that we have in physics a method for theory construction that has been proven effective over the last 50 years, but there is still some coincidences that it cannot explain. Some of them we might be on our way to explaining, but the other ones might resist explanation for another 50 years or maybe even more, or perhaps it's time for a paradigm change. So,
Thank you, Victor. Thanks a lot for this fantastic talk, also for the truly remarkable effort to make it very understandable and very resonant to our ears. We really appreciate it. We were really anxious for hearing your talk, but it was absolutely perfect. So we give the floor to Richard, who is the primary discussant of.
Thanks. So my understanding.
Do you want to share something?
No, I'm fine. So, my understanding of the discussant is that I basically put out some ideas as a little bit of a summary to start the conversation. So I think the first thing is that, with us discussing this, it was interesting that, the Christmas edition of the New Scientist had an article called "What a Coincidence." Okay. And in that, sort of the subtitle was "Seemingly Impossible Events happen all the time. Okay, and I think that's a nice backdrop. So if I'm a physicist, and therefore the third thing I'm going to do is make a spherical cow, okay, and sort of come on from what the talk said and come up with 3 possible whys, which you've sort of hinted at here. I didn't use such grand titles, okay, but you know, there. So the first one I've already sort of hinted at is the sort of random events, okay, the synchronicity, in terms of, you know, that one of the reasons why there may be these seemingly very strange coincidences, or very lucky, or very fortunate, depending upon the sort of emotion you attach to it and so on, is of course is that there's actually an awful lot of parameters or numbers out there, and they all have to go somewhere, and therefore some of them will line up in what looks like a very strange way. Okay, and you know, that of course is one possibility for why they're actually there. The other thing would be some sort of by design, or by intelligent design, if you want to allocate something even further, which is of course that there is actually the pattern that you think you see might actually mean that the pattern actually has something and is set up by whatever intelligent design is, which I wouldn't even imagine to try to explain that. So, you know, and I think you put this in earlier in the talk as meaningfulness, okay? And of course, whether there's any meaningfulness in that, of course, is a very interesting question. And the last thing I would put under the category of essentially survivor bias, and I think you had it under there as the anthropological principle, okay? And the traditional example of this is sort of, you know, when they plotted up the bombers that came back damaged from their bombing raids, and they plotted it up, and then they thought, oh, in the places where lots of them came back with lots of damage, we really need to put the reinforcement there. Whereas actually, of course, the ones that came back with damage in certain places are the ones that didn't crash. So, you know, actually, it's the damage that you didn't see is the one that you need to protect against. So why am I telling you that? Because that's nothing to do with this. But, you know, at the same point, you know, we can only observe one universe, probably. Okay? At least we have no way of understanding whether we can observe a second or a third or many universes, or whether there's an infinite number of universes, as you pointed out, as a possibility, which you can certainly think through as a thought experiment. Okay, but we can only really observe one, and therefore we observe a galaxy, a solar system, and so on. And actually, we know that it works for us, and we know that we exist in a certain way that we exist. Okay, and therefore maybe the reason why we observe these coincidences is coming back to the fact that they have to match up, because otherwise we wouldn't exist in the form we are. Okay, we wouldn't be along a sort of a carbon-based life form. We wouldn't be based upon water, etc., etc., etc. So again, you're coming to the point that this is coming from the fact that what we observe is then requiring these coincidences to be what's there, simply from the fact of what you observe. So I think those are, you know, the 3 possible whys that I see as different directions on that. And I will hand over to the discussion with that.
Thank you. Thank you very much for this very useful summary that works a little bit as a translation also.
Yeah,
into a wider discussion.